Gases diffuse at different rates, and this has well been done by a scientist who is long gone called Graham. And this scientist came up with a law called Graham's law of diffusion. And he says that under the same conditions of temperature and pressure, the rate at which a gas can diffuse is inversely proportional to the square root of its density. This is Mr. Ngata, your online tutor, ready to introduce to you a very good example that can help us understand how we can compare the rates of diffusion of different gases at particular conditions given in the question. So Graham began by telling us that the rate at which a gas can diffuse varies inversely to the square root of its density. So it tries to give different ways in which any calculation involving this rate of diffusion can get done. And if he begins, he says that the rate of, for example, at which a gas A diffuses over the rate at which a gas B diffuses should be equal to the square root of the density of gas B over the density of gas A. And he also says that the rate at which a gas A will diffuse over the rate at which a gas B will diffuse is also equal to the square root of the molecular mass of gas B over the molecular mass of gas A. That means when the rate of diffusion is high, then that means we need to look at this. This is rate of A, this is rate of B. This is density of B, this is density of A. So the rate is low, the density is high. The rate is high, the density is low. So the rate is high. The speed at which that gas moves in terms of its diffusion is very high. That's why it appears on the numerator side of this arrangement. And that means it must have a very, very low density. And if the rate is low, appearing at the bottom of this fraction, getting served as the denominator, we'll be able to get related to a density which is very high, appearing as our numerator. And as well, if the rate of a gas is very high, then that means it must have a very low molecular mass. If the rate of a gas is very, very low, then that means the molecular mass is greater. And we can also be able to say that the rate of A over the rate of B should also be equal to the time of A over the time of B. That means if the rate is high, so we can be able to have B, then A. So if the rate is high, then that means the time taken is going to be, let me just rearrange it here so that you can be able to understand. So if the rate is high and the rate is low, this will translate into the time being this over this. So the greater the rate, the smaller the time taken. The lower the rate, the greater the time taken. So rate and density are inversely proportional. That is correct. Rate and molecular mass are also inversely proportional, and rate and time are also inversely proportional. And that's what it says that the time of B over the time of A should be equal to the square root of the density of B over the density of A, which is also equal to the square root of the molecular mass of B over the molecular mass of A. So this is what Graham gave us in the work he did in terms of trying to compare the different variables or concepts to get captured in relation to the rates at which gases can diffuse through a porous spot or a particular opening. So I have a question here that I found from one of my archives in terms of the papers I always have to actually compile for the purpose of revision. And this question says 100 centimeters cubic of carbon 4 oxide, that is CO2 or carbon 2 oxide, takes 30 seconds to diffuse through a particular opening. Okay, and they're telling us that how long would it take 150 centimeters cubic of a gas called nitrogen 4 oxide or nitrogen dioxide to diffuse through the same porous spot. And you're told that the atomic number of carbon is 12, the atomic mass, and that of nitrogen is 14, and that of oxygen is 16. Now, you see, we can actually not say time of maybe carbon dioxide over time of nitrogen dioxide and you compare with density because we do not have the density. So this and this cannot work. And if we decide to say time of B and molecular mass of B, time of A and molecular mass of A, it won't work well with us. Why? Because we are actually realizing that different volumes of these gases are actually getting put under consideration. So this can only work in terms of having time getting compared with molecular mass if the volumes they're diffusing through that porous spot is the same. So volume must be constant. But if the volumes are different, then that means time and molecular mass cannot get compared to get their known value in terms of the time of NO2 in relation to how long it takes to actually diffuse through this porous spot. Then it means we are going to first get the rate because we have been given different volumes and the time of one. Then we can use that aspect of comparing the rate of diffusion and the molecular mass of these gases because we've been given the atomic masses of the respective elements forming these gases. So let me get the rate of carbon dioxide. How do you get rate? You're actually saying volume that diffuses through the porous spot divided by the time taken. That can give you the rate at which that gas diffuses. So the volume is 100 centimeters cubic and the volume has to get divided by 30 seconds, the time taken. So the rate is 10 over 3. The rate of carbon dioxide is 10 over 3, that is R. Then we shall go to the rate of nitrogen 4 oxide, and this is going to be again volume over time taken. So our volume over time taken. So volume is 150 centimeters cubic, but we don't know what time is. So the rate of this gas is 150 over T. So I have the rate of carbon dioxide, the rate of nitrogen 4 oxide, and I can also get the molecular mass of carbon. So the molecular mass of carbon 4, so let me just check this all well. Okay, the molecular mass of carbon dioxide is now you know carbon is 12, that is CO2. So 12 plus 32. Why 32? One oxygen atom has a molecular mass of 16 and there are two atoms of oxygen. So that gives us 12 plus 32. That gives us 44 grams per watt per mole. Molecular mass of that gas. Then the molecular mass of NO2, it will translate into nitrogen is 14 plus 32 oxygen, which is 16 times 2. So that gives us 46 grams per mole. So just come here and say now, rate of carbon dioxide over rate of NO2 should be equal to the square root of the molecular mass of NO2 over the molecular mass of CO2. So rate and molecular mass are inversely proportional. So when the rate is high, the molecular mass is low. And when the rate is low, the molecular mass is high. So they are inversely proportional. So I know rate of CO2 is 10 over 3 divided by rate of nitrogen dioxide is 150 over T. That must be equal to the square root of molecular mass of NO2 46, molecular mass of CO2 44. So we will proceed and have 10 over 3 divided by 150 over T being equal to, so I shall say 46 divided by 44, 23 over 22. Then we shall get the square. So the square root of the answer, that gives us 1.0225. So 1.0225. So let's divide these two. So we have 10 over 3 divided by 150. Okay, over T, that answer must be equal to 1.0225. 0.0225. Guess all is well. Fine. Okay. So this is going to be 10 over 3. I'll push this on this side. Times t over 150 to be equal to 1.0225. So this and this will disappear. So we have t over 45 is equal to 1.0225. So times 45 times 45. So this and this will disappear. So our time t should be equal to, so this one times 45, it gives us 46.011. So 46.01 seconds is the time that nitrogen 4 oxide will take to diffuse through this porous spot if 150 centimeters cubed of that gas gets reduced into that porous spot to be able to diffuse through that opening. Thank you.